I'm Paul Hertz. Today we'll be discussing TESS, NASA's next planet hunter. TESS will discover thousands of planets around other stars and help NASA in its search for life beyond Earth.
I'm Sarah Seeger. TESS will find planets of all sizes. TESS will find planets of all sizes, bigger than Earth, around nearby bright stars, building on Kepler discoveries.
I'm George Ricker. Using the 4 ultra-sensitive wide-field cameras on TESS, the mission will look at millions of stars for small drops temporarily in brightnesses as there are passing exoplanets.
I'm Jeff Ellison, and TESS is currently down at the Kennedy Space Center, where we're doing the final preparations and checkout before we get ready to launch on a Falcon 9 rocket on April 16th. After we launch, we'll spend the first 2 months doing a checkout on orbit, make sure the satellite works properly, and then we'll begin an exciting 2-year exoplanet hunting mission.
Hi, I'm Felicia Chow, and welcome to NASA headquarters. Join in on the conversation by following us on all our social media accounts. You can also ask questions during this briefing by using the hashtag AskNASA. And you can learn more about TESS on our website at nasa.gov/TESS. Before we start the conversation, let's learn more about this wonderful mission.
In the last few decades, we have found thousands of worlds around other stars. A new NASA astrophysics mission will help us find many more.
TESS,
Well, that
the
was
Transiting
distracting.
Exoplanet Survey Satellite, is NASA's newest exoplanet mission. It's being led out of MIT, and it's going to find thousands of new planets orbiting bright nearby stars. And it's going to build upon the legacy of the Kepler mission, only it's going to focus on nearby bright stars that are sprinkled across the whole sky, and it's going to help us answer a really important question, and that is, which of our near-stellar neighbors has planets?
During its 2-year survey, TESS will look for signs of planets, ranging from Earth-size to giants larger than Jupiter. TESS will search for these new worlds, or exoplanets, using transits, the same method as the Kepler mission. As a planet passes in front of its star, it blocks some of the light, causing a slight drop in brightness. TESS can detect those subtle dips and even use them to determine some basic features of the planets, such as their size and orbit. Each of TESS's cameras has a 16.8 megapixel sensor covering a 24-degree square, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a vertical strip of the sky, called an observation sector.
The coverage of the TESS cameras is unprecedented in terms of the amount of sky that they can actually see at any given time, and also their ability to cover such a broad portion of the sky. The types of targets that TESS will allow us to find will enclose essentially all of the bright nearby stars.
TESS will watch each observation sector for about 27 days before rotating to the next one, covering first the south and then the north, to eventually build a map of 85% of the sky. This coverage, about 350 times what Kepler first observed, will make TESS the first exoplanet mission to survey almost the entire sky. TESS will fly in a highly elliptical orbit that maximizes the amount of sky the spacecraft can image and is carefully timed with the orbit of the Moon. It will spend most of each 13.7-day orbit collecting data, and then, as it passes closer to Earth, it will transmit that data to the ground. Because TESS's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope, which allows the 2 missions to work together to first find and then carefully study exoplanets. Since most of the exoplanets found by TESS will orbit bright stars, missions like Webb will be able to measure the spectra of starlight absorbed by the planet's atmospheres, which can indicate what they're made of. Ground-based measurements of the TESS exoplanets can determine their masses. Combining the masses with TESS's size measurements reveals densities, allowing scientists to better understand the exoplanet's compositions.
The thing that we're really excited about with TESS is the way that it'll actually build on the momentum that we started with Kepler. So TESS is going to take that same search approach, but apply it to the vast majority of the sky, which still hasn't really been looked at in detail when searching for exoplanets. And by focusing especially on planets that orbit bright nearby stars, TESS allows us to start looking at things like planet composition and atmospheric makeup. And that'll then be crucial when we want to start looking around stars that are even further away and in deeper parts of the galaxy as well.
TESS is the vanguard of a new era of exoplanet study and will forever expand our understanding of worlds beyond our own.
So Paul, can you tell us more about how TESS is going to help NASA's search for life in habitable worlds?
Sure. TESS is going to look for planets around other stars by watching the slight dip in brightness of the star as the planet passes in front of it. And this will tell us which stars we need to look at to study those planets in more detail. So we'll be able to turn other telescopes towards those stars, like NASA's upcoming James Webb Space Telescope. And with those larger telescopes, we'll be able to look for telltale signs in the atmospheres of those planets that might tell us what the planets are made of, and perhaps even whether they have the kinds of gases in their atmospheres that on Earth are an indication of life. TESS itself will not be able to find life beyond Earth, but TESS will help us figure out where to point our larger telescopes in that search.
Sarah, so besides the field of view, what's the major difference between Kepler and TESS and the planets that they find?
Well, Felicia, the major difference is that Kepler, pioneering Kepler, was a census mission, essentially discovering and counting planets of all sizes and orbits, planets and stars that are quite far away. TESS is the natural next step by searching for planets around very nearby bright stars so that we can do the follow-up measurements, partly that Paul was talking about. And by doing those measurements, we hope to actually identify all the worlds we've been dreaming about, such as hot super-Earths that may have liquid lava lakes, or water worlds that may be 50% or more by mass water, like scaled-up versions of Jupiter's icy moons, or even rocky worlds of all different kinds, and even maybe ones that have atmospheres, thin atmospheres, reminiscent of Earth's. I should emphasize, though, that TESS's sweet spot is for planets transiting small stars, small red dwarf stars called M-dwarf stars that are half the size of our sun or smaller.
Jeff, can you tell us about some of the more exciting components about the TESS spacecraft?
Yeah, sure, Felicia. I happen to bring TESS with me, or at least a small facsimile. So it's not really this small. It's about 700 pounds. It carries about 100 pounds of fuel on board. And you can see there's a graphic that shows you how big it is with some people around it. It's a little shorter than I am. So the most important thing about TESS that you've been hearing about already is the fact that it has these 4 really cool cameras. They were built up at MIT, and they're the ones that this is the cameras that do the science. This is where we find the exoplanets. So the cameras in the center, to give you an idea about how big they are, this is one of the lenses that didn't pass inspection that would have gone in one of our cameras. And so this gives you an idea. There are 7 lenses inside each camera to bring all the starlight into focus so that we can collect the photons to learn about the exoplanets. So beyond that, there's a shade around the outside of the cameras, keeps the sun and the earth light and the heat of the sun from getting in where the cameras are so that we can get a nice clean view of the sky without any interference from other light sources. And then if you look around, it's got solar panels like almost every other spacecraft. And another feature that stands out is this large antenna. So we spend about 2.5 weeks staring out at the stars, collecting data about transiting exoplanets. We've got to get all that data to the ground. So we swing by the Earth, and this large antenna allows us to downlink all of that data very quickly down to the Deep Space Network at NASA to collect our images so we can then go around and collect more science data. The only other thing to point out is down on the bottom, we've got a propulsion system. Again, we carry about 100 pounds of fuel. This helps us get to our final orbit, which then we can remain in a stable orbit for decades once we achieve it.
Thanks, Jeff. So George, can you tell us about what inspired the TESS mission?
Yes. Beginning in the 1990s, our research group at MIT began developing sensitive X-ray cameras for a variety of missions. We were fortunate enough to fly on 2 Japanese astronomy missions, the Chandra Great Observatory from NASA, and a small explorer also from NASA called the High Energy Transient Explorer. And one of the things that characterized all of these missions was that they were using CCDs at that time that were large. And so our project was to make the transition from those CCDs of the size that we had there, which actually weren't much larger than the CCD that you have in the back of your iPhone. And we went from that to CCDs that have sizes that are more like these. And as you can see, this is a wafer that was actually used to fabricate the actual CCDs that Tess is flying. Not this particular wafer, of course, because it's got my fingerprints on it. But the size is identical. And one of the things that you can see is because of the lithography patterns that are in it, makes a really nice series of colorful diffraction patterns. The 8 rectangles that you can see in this wafer are the exact size of the CCD, so they're more than 100 times larger than the ones that you have in your iPhone. And a single wafer this size could actually, in principle, provide the CCDs that are needed for 2 of the test cameras. We've got a total of 16. We had pretty good yield, but not quite enough that we could do it all in two wafers.
Thanks, George. So Sarah, we know that Tess is going to measure dips of light as planets go by a star. But how do we know that the dip of light is actually caused by a planet versus, say, maybe a small star or some other object?
Well, the Tess science team will be working very hard to discriminate amongst light curves that are not from planets versus ones that are from planets. And believe it or not, in the field of exoplanets now, we have this down to a science. Because of Kepler and many other transit finding surveys, mostly from the ground, have really sorted this out. So we monitor stars long enough to try to see at least 2 dips in brightness so we can put it on a single planet. And we actually have been training a team, ourselves a small team of people so far, on simulated data. That includes like binary stars and instrument artifacts and other things that would not be planet candidates. And we use humans and computers to look at the light curves and other data products to practice finding the very best planet candidates for further study. And that's what we'll be doing as soon as we get the real data.
That's very exciting. So in the video, it was shown that Tess's orbit actually coincides with the moon. Jeff, can you tell us a little bit more about that?
Sure, Felicia, and it's an orbit that hasn't been used before. So we're going to be in a unique first-time orbit that I think other missions in the future will end up using, where we're synchronized with the moon. So the idea is that the satellite is traveling between near the Earth and out to the distance of the moon twice every lunar month. So every 2.5 weeks, it comes back through by the Earth. You can see in the video there, swings by and then swings back out. And the goal is that by swinging out to the lunar distance, you can see that the moon is orbiting around the Earth once per month, and the moon is tugging at the satellite. So it tugs it one way, and then as it comes around the other side, it tugs it the other way. And what that means is in the end, we stay in a nice stable orbit for decades with no fuel. So the fuel I talked about before is really to help us get to that orbit. Once we're in the orbit, we can survive for decades without any additional propulsion, which makes it a great thing for science. You can continue to do science for a long period of time. So we can stare at the sky for 2.5 weeks at a crack. We collect up all this exoplanet data that Sarah was mentioning, and then we swing back by the Earth. We stop doing science, and we point that big antenna down to the Earth. We get all those images down, and then we swing back out for another 2.5 weeks. So the orbit is incredible, not only because we don't need to have propulsion once we get into that stable orbit, but also because it's great for viewing the sky and being able to do the exoplanet research for, that we're destined to do here.
Thanks, Jeff. So, George, what will a Tess science image look like, and how soon will the science data be available?
Okay, well, one of the things that we did on a very cold night in January in Cambridge from the roof of one of the buildings at MIT is to take an engineering model of our camera up on the roof and just try to see how well it would do. And the image that you're seeing is exactly what we did see in a 2-second integration. So it gives you an immediate feeling for how powerful Tess will be in terms of looking at thousands of stars in every single field. That's what we're seeing here. and in millions of stars around the entire sky. One of the things that is characteristic of TESS is, by design, the cameras actually respond to a much broader range of light, in fact, even going out into the infrared. And because of the way the cameras were optimized to look for red stars in the way that Sarah described, 90% of the stars that we know of in the Milky Way are redder and cooler than is our sun. This is exactly the thing that we wanted to do for this particular mission. So as we move forward with it, we expect that once we're in smooth operation, that the TESS science images will be released about 2 months after they're acquired and they're deposited at the MAST archive at Space Telescope Science Institute.
Paul, why can't we just send a probe to an exoplanet?
Well, Felicia, the stars are very far away. Even with the fastest satellites we have now, it would take tens of thousands of years for them to get to even the nearest star. And the stars that we'll be looking at with TESS are many times further away than that. So since we won't be able to travel there ourselves, we're going to have to make do with studying them remotely from near the Earth and the Moon with satellites like Kepler and upcoming TESS satellite.
So, as you know, all these beautiful exoplanet videos and illustrations we have are all really just artist illustrations. So why is it so hard to directly image a planet?
So the reason is that planets are much fainter than stars. The Earth is over 1 billion times fainter than the Sun. And in addition, from a distance of light years away, the Earth looks really close to the Sun. In order to take a picture of a planet, instead of taking a picture, excuse me, let me just rephrase that. In order to detect the light from the planet, instead of just detecting the light from the star, we need a very special kind of detector that can block out the light from the star and leave the light from the planet right next to it. And the kind of camera that can do that is called a coronagraph. We've started building those and putting them on telescopes on the Earth. They can block out the light to see planets as close to stars as, say, Neptune is to our Sun. But if we want to see planets as close to their star as, say, the Earth is to the Sun from a distance of many light years away, we're going to need more powerful telescopes and better designed detectors than we have right now. NASA's next great observatory after the James Webb Space Telescope would be the WFIRST mission, and it will fly a demonstration coronagraph on it that would be capable of detecting planets like Jupiter around stars like the Sun.
So thank you all, and before we go into the Q&A session, can we go around for some closing thoughts from each of the panelists, starting with Paul?
Well, I'm very excited that we are now following up the Kepler mission with the TESS mission. Kepler will be running out of fuel sometime this year, and so it's perfect timing that we'll be launching TESS to continue the great activity of looking for planets around stars other than our Sun and thinking about what it might mean for life in the universe.
Well, what I'm excited about is, just backing up for a moment, when exoplanets was first starting as a field, we characterized individual planets to the best we could. Then with Kepler, the community astronomers were able to find thousands of planets, many with very little detail. And what we're all looking forward to now is like marrying these two fields, having a lot of detail on specific ensembles of planets over and over again so we can move the field forward. But mostly what I'm looking forward to is just getting the data.
So I'd like to sort of, not exactly contradict something that Paul said, but just sort of extend from it a little bit more. It's true enough that these stars and the planets that we're going to discover, although they're relatively nearby, it would take a long time to get there. The thing that I think about a lot when I consider the long-term historical implications of TESS is that there are 100 stars within 20 light years of Earth that likely have planets. And if you could travel at 20% of the speed of light, which people, it's a little speculative, and maybe this doesn't happen until the 22nd or 23rd century, I think there's a high probability that many of the stars and planets that they're going to target are going to be the ones that have been discovered by TESS.
That's cool.
This will be robotic missions, not people, but I think the idea is the same.
So, and I guess my excitement, I'm definitely excited to see this thing launch after 5 years of working on it. But I think one of the things I think about is with every NASA mission, we try to engage the public, right? You want people to understand, why are we doing these missions? What's the science of the mission going to help us learn about the universe? And one of the things about TESS that we thought about early on was, how could we engage young people? When I was young, nobody had ever seen an exoplanet. We didn't even know there was maybe such a thing as an exoplanet. We might be alone as far as planets in our solar system, might be the only one. So what we did is we put out a call to kids around the world to say, hey, why don't you draw pictures of exoplanets? What do you think an exoplanet would be like? And I think that the goal was to have kids start thinking about this idea that there could be planets around other stars and that there could be life out there. So you see some pictures here of exoplanet ideas we got from children from around the world. So the goal was to collect them all up. We put them on a thumb drive. We took it down to Cape Kennedy and we glued that thumb drive onto the bottom of the satellite so that all those children's exoplanets will fly with TESS when we launch on April 16th. And if you're out there and you're like, oh man, that sounds so cool, but I missed my opportunity, we do have still, on our social media sites, we do have the ability for you to continue to send in your pictures. So if you really want to draw us an exoplanet, what you think it would look like, send in your exoplanet drawings, and we'll make sure they get up on our social media sites so that everyone can see them. We're kind of building a gallery of all the photos. So that's part of what excites me, is that idea of kind of engaging the public and getting people to start thinking more and more about exoplanets and what we might discover.
Thanks, Jeff. Now we're going to go ahead and move into the Q&A session. First, we're going to go to questions on social media. We're going to answer 2 questions, and then we're going to go to the phone line. And then from there, if anyone in the audience would like to ask a question, please raise your hand and we'll give you a mic. So for those who are watching online and you'd like to ask a question through social media, please use the hashtag AskNASA. So Kendra, what do we have on social media today?
So we have a 2-part question from Sky, and he's asking, will TESS also be taking photos for potential evidence of life on the newly found exoplanets? And if so, what will be used to find any sort of heat or life signatures?
TESS, as we mentioned, it's a finder. TESS is a discovery mission. TESS will find thousands of exoplanets, but TESS does not have the capability to look at the atmospheres for signs of life. And that will be the James Webb Space Telescope, when it launches, will be capable of doing so.
Thank you. Can I ask one more?
Yeah, sure.
So I guess this is a good follow-up. Other than helping TESS find signs of life, what other things will James Webb do to help TESS or work with TESS once it's launched?
So the James Webb Space Telescope is a very large telescope, right? George showed how the size, or I guess Jeff showed the size of one of the, George showed it. Whoever showed it. Right, we have the size of one of the lenses on the TESS cameras over here. And it fits in the palm of your hand. The James Webb Space Telescope's set of mirrors comprises a collecting area that's over 6.5 meters across. So it is much more capable of collecting lots of light and dividing that light up into signals that allow us to learn things about the sources that it's looking at. So one of the things it will be doing is looking at the planets that are discovered by TESS. Since we can't see the planets themselves, we'll be looking at the starlight as it filters through the atmospheres of those planets, if they have atmospheres. And James Webb has on board spectrometers, which can divide the light up into its constituent colors, and we can see what kinds of gases might be in those atmospheres. And so that is how astronomers will be able to use the combination of TESS and James Webb to advance our understanding of not just how many exoplanets there are, or how big they are, or how far away they are, but maybe what are they made of? Are they the lava worlds? Are they water worlds? Are they rocky worlds with thin atmospheres like the Earth? And do they have atmospheres that look like our atmosphere or look completely different? That's what we're going to learn, and we don't know the answer to that question yet.
Yeah, just as another point to Paul's expression, the fact that the TESS planets are going to be on average 10 times closer than the ones that were discovered by Kepler, it means on average they're going to be about 100 times brighter. So if you tried to do with a telescope like Webb, these kinds of observations from the Kepler targets, 6.5 meters wouldn't do it. Paul, you'd have to figure out how to make a 65-meter telescope in space.
Working on it.
So, and I think just from my standpoint, one of the most exciting things is when James Webb or Next Generation Space Telescope was first being designed, no exoplanets had been found. So it wasn't part of its primary mission when we first started to think about it. So the idea that this whole evolution of exoplanet research has happened within the time frame that we've been working on the telescope, and that we've been able to kind of reuse it and say, hey, here's another way you can use this incredible tool to help us learn about exoplanets, has been a really cool thing for the agency.
So now we have a question from a reporter on our phone lines. Mike Cole from Spaceflight Insider.
Yes, hello?
Hi. Go ahead and ask your question.
Yes, my question is for Dr. Ricker. How are the CCD cameras that you developed at MIT new or special or different from the ones that, say, a backyard astronomer might use in their backyard telescope?
They are significant both in degree as well as in scale. One of the things that is for the typical CCDs that are used by amateur astronomers, I mean, I happen to have been an amateur astronomer myself, and I know a little bit about how wonderful the work is that amateurs can actually do, even following up transiting exoplanets, is the CCDs that you can go out and buy are typically very thin in terms of the way in which the light can actually interact because of the photosensitive depth. They're of the order of 2 or 3 microns typically. The test CCDs are 100 microns thick, and that's how we're able to actually get out into the near infrared and actually see the peak of the emission that occurs from the cool stars that test is going to be optimized for. The other difference is that the CCDs that were especially developed for tests have extremely low noise. We're able to push the noise down a factor of 10 below what Kepler actually had with the electronics that were available at the time that they were designing their instrument. And also the pixels are quite large, as you could see from the wafer that I showed.
So next, we're going back to social media, but if anyone in the auditorium would like to ask a question, please raise your hand and we'll get you the microphone. So we'll go ahead with social media, and then we'll directly go right after to the audience.
Sure. Benjamin is asking, can you expand on how TESS will build on Kepler's discoveries?
Well, Kepler was the first of its kind, really. And Kepler found all sorts of planetary systems we didn't expect, like compact multiple planet systems and these super Earths that are very close to the star and so many things. But how TESS will build on it is, first of all, we have an idea of what we're looking for, and we'll know which systems, when we find them, that we can jump on to follow up, to look at their masses, get a mass for them, and look at their atmospheres, and just learn a lot more about them. The main way we're building on is just sort of more logistical or programmatic, because Kepler ironed out like a ton of wrinkles on how you go from all that data and the light curves and detrending and finding drops in brightness and associating those drops in brightness with planet candidates or just with junk or stars or other things. So there's 2 ways we're building on Kepler.
Okay, so we're actually going to take one more question on the phone lines, and then we're going to go to audience. So we've got Steve Gorman from Reuters. Steve, are you on? Steve? All right, well, we'll hold off on that question. Let's go ahead to the audience.
Maximum angle of the exoplanet system that we see it? What's the effect of that on the probability?
Well, that's a good question, because we all just forgot to mention that transiting planets that go in front of the star and cause that drop in brightness of the star, they have to be lined up almost perfectly. So let's say 90 degrees or 87 degrees or, you know, maybe a little, but it's that very tight range. But we're assuming, and we think we know, that all star systems with their planets, they have a random inclination that they're born at. So we're not seeing most of them, unfortunately. And the ones we are seeing are just aligned properly.
That's one way we're looking at the systems around cool stars is very helpful to us, because on average, the planets that we're most likely to be interested in that are in the so-called habitable zone are going to be relatively close to their host star, and that increases the probability that you'll get a transit by a factor of 2 or 3, which is helpful in getting many more candidates than we otherwise might get.
Just to add one more detail, we're less worried about the systems we'll miss entirely because they're not transiting. More concerned if you see one planet transit, are there more planets in the system? And because the test stars will be so close, we can use other techniques like radial velocity to look for other planets in the same system even if they don't transit.
Thanks. Now we're going to go ahead back to Steve Gorman from Reuters. Steve, are you on?
Yeah, I just pressed star 1. Nothing happened.
Oh, well, glad to hear you. You have a question for us?
Oh. Yes. Hi. Thanks for taking my call. Sorry. So my question is, I believe that NASA said that they expect that they will find 300 or so Earth-sized or super Earth-sized exoplanets with tests, which are. And my question is whether the fact that they're Earth-sized or super Earth-sized does that make the likelihood that they might be habitable for life greater than otherwise? And also, of those 300 or so or 500 or so you expect to find, how many of those might actually be in the so-called Goldilocks zone?
Well, I'll answer the first part and I'll leave the second part for George after. But what's so great about TESS in the sort of era of exploration of exoplanets is we don't have an answer to your question. We're going to answer that. The question is an Earth-sized planet habitable? That means, does it have liquid water or water vapor in its atmosphere? Or is a super Earth size 1.5 times or twice? Does that be potentially habitable? We're going to find that out by getting the sizes and masses and atmospheres. So we can answer that question for you later. We don't know the answer in advance.
Yeah, we've done a series of simulations. There have been some very clever MIT graduate students who tried to answer the question through simulation, but we're really going to know the answer to that within a few months after we launch.
And just to add one more item to what George was answering was about how many planets in the actual Goldilocks zone. As the field evolves, the concept of the Goldilocks zone is also evolving. If a planet has a very massive atmosphere, it's going to be in a different, it could still be habitable even if it's not in the Goldilocks zone. So we have to ask you with that excellent question to wait until a couple of years from now when we can give you a real answer.
Thanks, Sarah. We're going to go back to the audience for any other questions. Oh, there we go.
Hi. The thing that was so powerfully simple about Kepler's planet finding strategy was it looked at just one part of the sky for a very, very long time and looked for these variations. TESS, of course, is going to open up the whole rest of the sky, or most of the sky, in this survey. But that means that the strategy for finding planets is different. You're not looking at the same stars for the same amount of time. So, I mean, talk to me about the strategy, about how you're going to use that difference. And is this then optimized for only finding planets with very short orbits?
Well, I'll answer a portion of that. You're right. I mean, in order for Kepler to look for Earth-sized planets orbiting at the distance of the Earth around a solar-type star, the strategy that Kepler used was spectacularly successful. The way that TESS is actually looking at it by using these, looking at these stripes in the sky for only a lunar month, allows us to look for planets orbiting cooler stars for which the year in that system might only be 10 days or 2 weeks or so. But in addition, the area at the ecliptic poles that TESS will actually stare at continuously, first the south and the north, over the 2-year primary mission, that period will be for a year and will be able to extend to observations that will be ideally situated for Webb to look for atmospheric structure in those particular planets.
So yeah, just to summarize, it's basically the same strategy with a few more complexities added on.
Yeah, and of course the idea that the planets are associated with brighter stars is going to make everyone's life easier. So you're not. I won't blame Paul about the 6.5 meter telescope, this tiny thing that's called Webb. But for ground-based observers, it's the same thing, because they're pushing right now to build 30 and 40 meter telescopes. If they were to try to work only with the planets that were the bulk of the planets that were discovered by Kepler, they would be talking about having to make 200 or 300 meter telescopes for the ground. So it's a similar problem. So we're trying to help everybody.
We're going to go ahead and answer a couple of questions on social media, and depending on time, we may stay on social media. So Kendra, go ahead. What do we have?
Sure. Nicholas wants to know, will TESS be sensitive enough to detect planetary ring systems around exoplanets?
Haven't simulated that yet, George?
Well, I think things like Tabby Star, for example, which people may know about, TESS will certainly be able to find systems like that. It depends a lot on what the ring structure, whether there are clouds of asteroids. I mean, there's a lot of speculative ideas, but that actually brings back something that I think we're all acutely aware of. I mean, TESS is an explorer mission. There's a huge discovery space that is going to be opened up for the first time by TESS. I mean, Kepler looked at a 0.25% of the sky, and that meant that the discovery space is there for the other 99.75% of the sky. So I think that's the real promise that I think TESS actually has.
And even if we don't have an exact answer for you, I mean, the real answer is probably the rings have to be pretty big. However, all the data is made publicly available through the MAST archive, and anyone can look at the data. You could be a very sophisticated user, or we believe our data will eventually end up on crowdsourcing platforms like Kepler's did, so kids and stay-at-home parents and retired engineers and everybody in between can actually be searching for rings and other things.
We have about enough time for 2 more social questions.
Sure. Kumar would like to know, how will we here on Earth benefit from TESS's research?
Well, TESS is helping us explore our place in the universe. People have always wanted to know, are we alone in the universe? Up until 20 years ago, we didn't know of any planets beyond our own solar system. Now we know that at every star in the sky that you look at, there's probably a family of planets around it. And most of them probably have rocky planets in the habitable zone. So we've expanded our understanding of our place in the universe. Missions like TESS will help us keep learning so that eventually we can answer the question as, are we alone or we just have the best prime real estate in the galaxy?
And I'll just add a more practical answer to that question too, and that is that it takes a huge amount of pure science to enable really like life-changing discoveries like GPS or lasers or medical imaging. And there is actually a whole collection of lists there. But what I like about exoplanets is it's just, people love exoplanets. It's not, interstellar or Arrival, not yet anyway, but it draws people into science and it helps with STEM education and keeping the pipeline moving forward, not so everybody will work on exoplanets, but so they'll go into other technology areas and industry and defense and other things.
Kendra, we have one more question on social media.
Great. So Mark wants to know, how will you assess whether or not the TESS mission was successful?
There's a formal requirement that NASA has called a level 1 requirement, and that means that the TESS team has to establish not only detections of transits, but measure masses for at least 50 planets that are of the size of what we refer to as a sub-Neptune. It's a planet that has less than 4 times the radius of the Earth. This requires that there not only be the detections that we're going to make from the images by actually seeing the dips in the light curve, but we then have to carry out follow-up observations, including spectroscopy that will actually allow us to look at the tugging of the planet against its host star, which causes tiny motions in the Doppler shift from any emission lines or whatever features that you get from the host stars. So that is another aspect of the program that we've been charged to carry out.
And that's all the time we have left. Thank you so much for joining us. If you have any more questions, please send them to us using the hashtag AskNASA. And be sure to check out our very cool interactive book and posters on the ABCs of exoplanets, and learn more about the TESS mission on our website at nasa.gov/TESS. Also, be sure to visit us on all our social media platforms. Thanks for joining us today. We'll see you at launch on April 16.